Let us start with the clarification of notation. We are intentionally showing you different notations, and I'm using different notations in class because different textbooks use different notations. So if I just get you used to one set of notation, then you will not be comfortable reading like Schwalms and Sandler and another textbook which you will encounter in your chemical engineering degree. So how you need to identify reading it is, let's just get comfortable with clarification of the notation. I'm not going to stick to one consensus of one notation throughout the course, but I'll use different notations to suit the different situations. Okay, so for example, going over the clarification of notation, I just want you to be aware that like maybe it will also cover some topics we've done in lecture 1. So for example, someone says, oh, I have h and h is a function of t and p, and you can go to that person, okay fine, I can give you a total derivative even though you haven't given me the full function yet, but I can go, therefore the total derivative is implied by dh is equal to dh, partial dh by dt, which is a function of t and p, your h, dt plus partial dh by dp, where h is a function of t and p dp. Okay, so let us just look at the partial and go into more of, let's just zoom in. We want to zoom in into this specifically and understand it a bit more. Okay, so I'm just looking at one, but it kind of applies to the other ones. So just looking and zooming in the partial. So say we just want to understand notation. So that's fair enough. This comes from my total derivative, where h is a function of you partially differentiate h with respect to t, okay? And in my partial, you can see here that h is a function of t, keeping p constant. So that's how you got your total derivative, is where you took, okay, h is a function of t and p, I would need to partially differentiate h with respect to t, keeping p constant, times my differential, and then partially differentiate h with respect to p, keeping t constant, times my differential, and that's your derivative, right? So this is also equal to partial derivative of h with respect to the partial derivative of t, pt. It doesn't really matter the order, okay? So as long as you can read the notation that, oh, okay, so I have pt here, that means if t is here, it means that this h is a function of t and p was kept constant. It's also equal to the partial derivative of h to the partial derivative of t, brackets p. Okay. It's also equal to dh by dt, keeping p constant. But you see, in order to change from a differential into a partial, you keep p constant. So that's just another way in which you could write this in terms of a partial. And now we're going to just go upside down. So it's also equal to 1 over the partial derivative of t by dh, keeping p constant. So this equation here is the same as this equation here, okay? Because when you bring it up, it's the same thing. What is it also equal to? Yes, it's also equal to 1 over, I'm going to leave out my brackets, the partial derivative of t with respect to the partial derivative of h, but now, as was picked up, it's now t is a function of h and p was kept constant. So this is different ways and forms in which you will see your partial derivative. What you can see, there's a common theme, is for this specific partial derivative is p is kept constant in all of them. I know some colleagues that have just preferred the bracket method for some situations and have preferred the superscript notation for other ones. Okay, so in essence what I want you to draw from this is that when reading the superscripts, it's attached to that h, where it's saying h is a function of t and p, or it can be also a function of p and t, but you can see that p is kept constant because it's nowhere in here. Alright.